Today, we'll be talking about how Jewell Instruments inertial sensors are a critical component for passenger safety, comfort, and train control for rail and metro applications worldwide. Accuracy and reliability are crucial for these sectors, and we'll demonstrate why our sensors are so widely used. We'll provide an in-depth analysis of Jewell Instruments' sensor solutions for rail and rail transportation by going through the common applications, their implementation, and what makes Jewell Instruments' inertial sensors uniquely effective for rail and rail transportation applications. We will also provide additional technical resources that will help you select the product that best fits your project. Rail applications by their nature demand rugged and high-precision accelerometers and inclinometers, as they may potentially be exposed to extreme rates of vibration and shock. Jewell has more than 50 years of experience in the design and manufacturing of a wide range of standard and customized sensors utilizing a variety of technologies and can be tailored to your specific requirements. If you want to learn more about what we do here at Jewell Instruments, we've linked further videos and our website in the description below. Jewell Instruments is a world-leading manufacturer of high-precision and reliable motion and tilt sensors. This broadly recognized excellence has led to Jewell supplying more than 35,000 sensors, which are installed on trains and rail systems all across the world. These are just a select few of the companies Jewell has worked with. Of particular note, our Railstar branded sensors have gone through rigorous third-party qualification testing for EMI, vibration, shock, and temperature. They meet both European Senelec and North American ARIMA standards. Our Railstar branded sensors include high-performance, force-balanced, and precise MEMS-based technologies. For more information, follow the link in the description of the video. There are three primary types of rail applications that our sensors are used for: maintenance of way, automated train control, and rail test and measurement. We'll go through each of these in the video. Rail maintenance of way is essential to keeping tracks working correctly. Both the smaller manual and the large machines used for this purpose require highly accurate and rugged solutions to measure low-frequency tilt. The fluid-damped mechanisms of our force-balanced sensors deliver superior noise rejection in high shock and vibration environments, as well as excellent output stability. From ballast regulators, rail grinder, lifter and tamper, track construction or renewal to track stabilizers, our LCF, LSB, and LSO series are excellent inclinometers for these critical projects. For decades, our LSBC, DXI, and more recently the LCA 165, JMA 165, and LCF 501 series accelerometers have been among the most essential devices in driver and driverless train automation and CBTC systems. They are used to measure position feedback, acceleration, and deceleration of high-speed and metro trains. Jewell Instruments sensors accurately determine train position using double integration and even accurately sense and account for centripetal and lateral acceleration in train systems. All of this is done with the passenger comfort and safety in mind, while reducing travel time to improve train performance. Testing and measurement are also crucial for any rail maintenance program. Inaccurate measurements could result in train derailment and loss of life. This important step cannot be overlooked, and this is what drives Jewell Instruments to ensure highly accurate sensors for railcar monitoring systems and automated rail profiling, to name a few applications. Our LCF, DXI, DXA, and new LSOX are rugged devices used for these applications to achieve a smoother and safer ride for all passengers. The photos on the left and center are examples of our sensors mounted in CBTC control systems for acceleration and deceleration measurements. The photo on the right is showing a piece of equipment used to measure and profile the rail-to-rail elevation differences for maintenance purposes. Jewell Instruments has a wide range of accelerometers and inclinometers used primarily in the control systems that are certified to European and North American rail standards. Force balance technology is reliable and precise for detecting acceleration and tilt with an incredible resolution of only 1 micro-G or 1 microradian. The sensing element is the torquer, a D'Arsonval mechanism, which is a coil of wire suspended in a magnetic field. And as a current is applied to the coil by an acceleration or tilt, it causes rotation of the unbalanced mass. This rotation is detected by the position sensor. Jewell Instruments has a variety of suspensions that we can implement depending on the application. The image shown here is called a taut band meter mechanism, and the coil is constrained to move only in rotation. The pendulum inside this torque motor wants to stay fixed in the inertial space, and as acceleration is applied, the unbalanced mass will move in respect to the position sensor, which triggers the servo amplifier to supply a current into the motor and restore the mass to its initial position. The amount of current that it takes to do that is directly proportional to the acceleration, or sine of the input tilt angle in the case of an inclinometer. The accelerometer is mounted along the train axis, so the sensing axis is in the direction of the train motion. Because gravity is also a downward force, the total acceleration output is a function of not only the forward and reverse motions of the train, but also subject to tilt with respect to the gravity vector. Thus, the total acceleration is a sum of the train acceleration plus gravity multiplied by the sine of track grade as shown on screen. In the dynamics of our sensor, we have an electronically controlled frequency response. The damping function is controlled one of two ways. For an undamped torquer, also known as a dry torquer, the frequency response is electronically controlled. But for higher vibration or shock applications, the sensor or torquer assembly can be filled with different viscosities of silicon fluid, which participates in the damping function. We can adjust the servo response to maintain a certain bandwidth up to 100 Hz. In some cases, the output can be adjusted to a lower frequency, and the characteristic of such output is second order. At the natural frequency, if you look at the dotted line where it shows 30 Hz, there's a 12 decibel per octave roll-off after the 30 Hz. The 30 Hz has a phase shift of 90 degrees for a second order system, and the damping ratio of the dynamics of this system is approximately 0.7 zeta, which produces a roll-off of 3 decibels down at the natural frequency. In many cases, that frequency is too high, as we want to have a high enough bandwidth to allow your control systems to measure the acceleration and deceleration, but also low enough bandwidth to attenuate strenuous noise and vibration. Our sensors are of such quality that even if the sensor is misaligned a few degrees due to incorrect installation, the error is extremely small, as shown in the table on screen. To help you visualize the data, this chart shows the roll-off of different types of dynamics that Jewell Instruments has control over in our sensors. Our accelerometers and inclinometers can be adjusted electronically, and, in some cases, we can adjust the viscosity of the damping fluid used in our torquer. Depending on customers' requirements on their control systems, we can tailor our frequency response dynamics to their specific system needs. Other errors can occur, such as the centripetal acceleration error, which is a function of the train velocity squared divided by the track radius. This is in the cross-axis of our sensor, and cross-axis sensitivity is kept as low as possible. In the example on screen, for a radius curve of 250 meters and velocity of 5 kilometers per hour, the overall error is only 800 micro-Gs, which is typically acceptable in control system environments. When a metro train is coming into a station, the train would need to stop at a specific location, as there might be automatic doors that will only open when the train gets to that exact position. Many times, the acceleration information is used from Jewell's sensors. If acceleration is integrated one time, the velocity can be obtained. If it's integrated again, you would get displacement. In such application, there would be a tag on the track around 60 to 100 meters out from the stopping location, and the control system will begin this double integration process to calculate the distance from the tag on track to automated doors on the metro platform. This can very accurately determine the train's exact position as the system begins the deceleration at the tag point and slowly brings the train to a complete stop at the ideal location. In this slide, we are looking at an example of rail maintenance of way and focus on the rail elevation angle and settling of the rails. Customers will have a database where the data logger indicates the elevation of the track from rail to rail and calculate the height difference. Jewell has sensors that have been developed for this application over the years with a maximum error of 0.2 degrees. This would equate to a maximum error of half a millimeter if the rail-to-rail distance is 1,435 millimeters. The attention to detail and highest quality standards are what set Jewell Instruments apart. We pour more than 50 years of experience in the industry into each product, leading to an astounding number of more than 35,000 of our sensors used in rail applications. Jewell Instruments sensors are rugged, reliable, high precision, and made right here in the United States of America. We offer a wide range of different customizations. Additionally, Jewell's RailStar sensors have been qualified to meet rigorous quality standards, including Senelec and ARIMA. But most importantly, we truly value our customers and work tirelessly to ensure satisfaction and success. We've linked these and further resources in the description below. Feel free to reach out to us with any questions you may have. Thanks again for watching, and we can't wait to learn more about your project and help you make sense out of motion.